So we're in Chapter 7, Pointers, but I tacked on some other stuff. As always, the PowerPoints should be used in conjunction with, parallel to the book. They cover material that the book covers, but they also wander off and cover other stuff too that I think is important. The lights are a little too bright up here. One of the first things I want to cover is the idea of the string functions in the string.h library. Now we could actually kind of write all these functions ourselves if we really wanted to. String length returns the length of the string, not counting the null character. We could write a little for loop that would check, And what terminates a string? What specific value? Null, a 0. So you would just keep counting characters until you hit a 0, and ta-da, you've got a string length function. And so classic programming exercises are to have the students write all the versions of the string library functions. String cat, concatenate, appends one string to another. String LWR makes everything lowercase. STR upper makes everything uppercase. CPY and cat and length are the ones that people most use most often. Maybe string comp, CMP, compare as well. Compares two strings. It doesn't just check to see if they're equal. You call string comp, you give it two strings, and it'll tell you, it'll return either a 0 or a negative value or a positive value. So you can check to see if something is less than, equal, or greater than. So the string cat function concatenates the source string at the end of the target string. For example, computing, with a space there, in techniques, once concatenated, would create computing technologies. Oh, well, take the space out there or put one in, right? Guess it's cooler to take it out. So generally the form is string cat, string 2, string 1. Concatenates, adds string 2 to string 1. So it appends string 2 onto the end of string 1. The first character in string 2 overwrites the character, the null character of string 1. So somewhere in here you've done, char A is equal to, jobs, and char B is equal to Steve. Then if you do this, string cat B comma A, well, jobs is JOBS followed by a null. That's what's in it. And Steve is SDEV, null. So when we string cat that one onto that one, the J replaces the null, and then the rest of them get added like that, including the null. And so that's our new string once that's done. With a null at the end. There are some problems here. B is only allocated to 5 characters here. So if we string cat A onto the end of B, how many characters did we need to hold the results? We needed, well, I'm sorry, when I said it was 5, it's actually 6 because it ends in a null. And this one, since it's 4, is 5 in length. So the length of this array is 5. The length of this array is 6, including the nulls. And when it's done, it would equal 1, 2, 3, 4, 5, 6, 7, 8, 9, plus one more, which is a length of 10. 9 plus the null. Well, that's not good. We're trying to copy something that's 10 long into something that's 6. The compiler's not going to catch that. It's not going to warn us. At least I don't think it will. But it'll probably blow up. It'll probably give us an error. We could test that out if we wanted to. So the big problem with string cat and string copy is that they don't do any safety checking, and they're happy to overwrite the
past the boundary. So typically what people wind up doing is creating a great big array, 80 characters long or something like that, and then they string cat all that stuff into there, and that's kind of wasteful of memory, but it's one way to do it. Another way would be to add the length of this one and this one together, and then allocate an array of that length. Now if you've been reading about arrays, or you remember, the array has to be defined with a constant. You have to say, I want an array that's 10 characters long or 11 or something like that. And you can't do that if you're calculating this stuff on the fly, right? You could call string length on Jobs and get 4, and call string length on Steve and get 5. But then you can't allocate that. Let's go ahead and do this. Let's go ahead and pop open some code. I'm going to open an old one and then copy it to a new one. I'm just going to call it T2.c. Alright, and I'm going to need good old Sigwin there. lst2.c, make sure it's there. Indeed it is. Alright. So, let's create two strings. Char fname. Fname array symbol, square braces, is equal to Steve. Char lname, braces, is equal to Jobs. And then let's create something called full name that's large enough to hold both of those. Well, we don't know how long those are. Can we just use string length to get a length and add 1 to that? Well, that'd be nice. It'd be cool if we could do this, but it's not going to work. Int length is equal to string length fname plus the string length of the lname plus 1 for a null. That'd be great, but it won't work. Why? Because the compiler insists that this value be a constant. So if I try to compile that, I'm going to get an error. CLT2.c, oh, excuse me, GCC T2.c. And it says len is undeclared. First use, oh, excuse me, len equals string length. And I get an error. No, I don't. Honest to goodness, you're going to let me get away with that? Wow, the Microsoft compiler would have complained all up and down about that. I'm impressed. We saw that the Microsoft compiler didn't even like it when I had a variable declared as a constant that I was trying to use to declare the length. Well then, okay. So supposedly that would work. Great. Let's string cat or string copy our stuff into there. So I'm going to do string copy, and I'm going to copy the first name into the full name variable. So the target goes first, and then fname. And then let's string cat the last name on the full name. So again, the target goes first, and then lname. And let's print it out. Printf name equals %s \n end quote comma full name. GCC minus capital WALL T2.c, and then /A to run it. And it printed out name is equal to Steve Jobs. What if we had more data that we wanted to append to it, though? Right now, it's about 10 characters long. We could prove that to ourselves with a for loop. Print it out. Let's declare an index counter, set it equal to 0. And let's do a do while loop, just because we haven't done them. So let's printf full name %d equals %d \n end quote comma I comma full name subscript I, and then I++, and after our closing brace we're going to keep going while full name subscript I is not equal to 0 or greater than 0. Either one of those would work. I'm just going to do not equal to 0, not equal to null. Null and 0 are the same thing. If you like doing that, great, but I'm going to leave it 0. So this should print it out, including the null. I wanted to see the null. That's why I made it a post-test loop rather than a pre-test loop. All right, and those are the ASCII values of the characters. And I didn't see the null. Well, shucky darn. I guess I'm going to rewrite the while loop. What could I have done about that? How about I take the I++ out of here and move it right here. That way the comparison happens and then it is incremented. I believe that'll work. GCC -wall t2.c /a to run it. There we go, and it printed it out including the null. So we can see that it's 10 characters long. Including the terminating null. But what if we wanted to add another word to it? Well, it's too long, it's too short. We couldn't tack on another word. Where I'm going with this is I want the idea of being to Malloc, a longer string. So say I wanted to add some extra word to the end of it. Not sure what. Not sure why I picked Steve Jobs either. He didn't invent the Z language. But I want to add the word Macintosh to the end of it. So I'm going to need a new length. So let's do length equals length plus strlen parentheses quote Macintosh. And let's allocate a new string. Let's create a new string. I can't think of a clever name for it, so I'm just going to call it SZNew. But it's going to be a pointer. Why did my brain just freeze on the idea of whether the pointer comes first or last? I think it comes before it. I think on a whole chapter I'd remember that. Yeah, it comes before it. Okay. So char start SZNew. Now I need to allocate enough memory to hold our new string once we concatenate the word Macintosh onto it. So SZNew is equal to Malloc, the length of the new string, len, times the size of a character. Character takes only 1 byte, but an int takes 4. And the double takes 8. So we have to allocate that much memory. So size of a char. Now we have enough memory to copy the word Macintosh onto it. I should say concatenate the word Macintosh on it. So string, no. I need to copy that full name onto it, and then I need to concatenate the next one. So string copy, and some people would zero out the array after they malloced it, because you don't know really how big it is. Nothing wrong with doing that. Or at least sticking a 0 as the very first character so that we can indicate that it's an empty string. That's fast and easy. Let's do that. SZ new subscript 0 is equal to 0. There. Now it's an empty string, right? It's got room for 20 characters or whatever, but the first one's 0, so all the string functions are going to assume that it ends right there. If we printed it out, it would be a string of 0 length. So we could string cat or we could string copy into SZ new our full name. And then let's string cat the word, string cat into SZ new, comma, the word Macintosh. And then let's print it out with a loop. I feel like just copying and pasting that do loop. I'm going to do that. I'm going to copy this loop, and I'm going to change all the occurrences of the word full name to SZ new. Why SZ? It's a string and it's 0 terminated. Okay, so I took that do loop, I copied it, I'm going to change every occurrence of full name to SZ new. Then I better walk around and make sure everybody's caught up. I haven't checked in with y'all. All right, I made a mistake. Anybody spot my error? Why did it start printing out SZ new at 10 rather than 0?
You never reset I.
I never reset I. Yeah. So I is equal to 0. I forgot that line. All right, and there it prints out Steve Jobs Macintosh.
If we wanted to prove it, all we have to do is change this %D to a %C, and we'd see the characters themselves rather than their ASCII versions.
What does Malloc do?
Allocates memory, goes out and grabs that many bytes of RAM, and returns a pointer to that memory. And after you malloc it and after you use it, and before that variable falls out of scope, you have to free it. Do you have to? Will the program crash if you don't? No, especially on a version that's simple. But it's called a memory leak. If your program continually allocates memory without releasing it, its memory requirements grow larger and larger and larger. Firefox used to be notorious for its memory leaks. The longer you left Firefox running, the more RAM it would consume. And you'd come back after a week and you'd check in on Firefox and it'd be using up like 3 gigabytes of your RAM or whatever. You close it and open it up, and then it's all nice and tidy again, only using 500 megabytes or whatever. So a memory leak is when a program allocates RAM with Malloc's RAM while never releasing it. So the very last statement in our code before the return statement should be a free.
So you made a pointer to your char, but the char normally is only 1 byte, so you made it bigger?
Right, but remember that a character and an array are the same thing. So char star SZ new is the same as an array. It's just that it doesn't have any memory that it's pointing to yet. So we allocated some RAM for this to point to. It's like we created the address, but it's not pointing to a house yet. And then we created a street full of houses
for it to start pointing to.
So if you make a char, it doesn't have any space in it?
Yeah, if it was just a character, it'd be big enough for one.
Oh, okay.
But we created this, it's not big enough for any characters. A pointer is completely different from the data that it's pointing to. This is an 8-byte value pointing to nothing in particular until we do something like this, or we do as z new is equal to ampersand and give it some value.
So if you put a pointer on the char, when you make it, it doesn't have any space.
Right, right.
But if you just do regular char, it has one.
Exactly. Right, right. So up here where we created some strings like that, yes, that allocated enough space to hold the word jobs plus a terminating null. And if we wanted to, we could put like an 80 there, and it would allocate it out to 80 characters, and then the first 5 of them would be the word jobs, null, and then the rest of them, who knows what it would be.
So if you have a char and it's only one long, are those also null terminated?
No, no.
So how do they know when to end it?
Well, a character is automatically one long, one and only one. A character by itself is not an array.
Okay, so the only reason strings are null terminated is because they don't know how long.
They have no idea how long it is. Right. In Java, yeah. In other languages where you can ask the string for its own length, that's great. This language, you have to end it in a null. If we're going to use some other kind of array rather than a character array, because you can use Malloc to allocate any size array. I mean, any type of array, an array of ints, an array of doubles, or whatever. It's only the strings that you're guaranteed are going to be null terminated. You could just make a pact with yourself. I'm always going to null terminate my other arrays, but 0 is a valid value, right? If you have test scores, somebody may make a 0 on it. You could use that as a terminating value. Is this working, or does anybody have a syntax here you want help with?
I have an error.
Okay.
Maybe you can use a really weird character.
Right. I've done that, like negative 99999, you know, something like that. Never going to have a test score equal to that. All right, so you could create any kind of array like that, not just an array of characters. So int number NA1 for number array 1, 10, like that. And we could set them all equal to 0 like this if we wanted to. That's one way to allocate an array. We could make a pointer to that array. Int star p for pointer, NA1, is equal to NA1. Now, anything we do to NA, anyway, these are both pointing to the same memory. We can access them the same way. Let's set this equal to 66. We could print that value out. Printf %d, \n, comma, NA1 subscript 0, or star p NA1. That both will point out to 66, print out the 66. Let's make the second value in the array 33. Printf %d space %d \n. Let's print out both values. NA1 subscript 1 is the same thing as saying star parentheses PNA 1 plus 1. And if you think about it, this is the same as saying, don't make this change, this would be silly, but putting parentheses there and putting that there to indicate that it's element 0 in the array. And this is element 1 of the same array. Now, this didn't make a copy of the data. They're both pointing to the same array. So if we changed element 1, or the first element, via one of these syntaxes, it would be the same for the next. We could kind of prove that to ourselves. It's 66 right now. Let's set the first element array equal to 99. NA1 subscript 90, NA1 subscript 0 is equal to 99. Equals, not double equals, 99. And I have a syntax error. line number 36. Oh, yeah, I guess there is. Okay. Like that. All right, and so when it runs, it's going to say that the first element was 99 and the next one was 33. Like that. So an array is a pointer, and a pointer is an array. Well, let's allocate a bigger array. Let's allocate a new array. NA1 is going to stay the same. We're not going to mess with NA1 anymore. But PNA1 is equal to Malloc, and how long do we want it? We want it to be 40 items long times size of int. Now we can store 40 items in there if we wanted to. For parentheses, I is equal to 0, I is less than 40, I plus plus, PNA, PNA1 subscript I is equal to I. That's going to copy the values 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 into it, all the way out to 39, which we could prove by printing it out. For I is equal to 0, I is less than 40, I plus plus, printf, %d space, end quote, comma, PNA1 subscript I. And then after that, let's just print out a \n. Okay. So that array should have all the values, consecutive values between 0 and 39. And that's what we see. And this is how we accessed it in array nomenclature, in array syntax, but let's access it via pointer syntax. I'm just going to put a star there and then a parentheses and make this PNA1 plus I. So starting at this memory address and then adding 1 to it, give us the value that's stored there. And maybe it's occurred to you, maybe it hasn't, that shouldn't work because ints are 4 long, right? They're not just 1 byte long. So wouldn't this just give us byte 1000, 1001, 1002, 1003, 1004? No, it doesn't. The pointer nomenclature actually multiplies this by the value, the size of the int. And I don't know how it does it, but it does. So this is equal to 1000, 1004, 1008, 1012, and so on. So these two syntaxes are exactly equivalent. PNA subscript I or star PNA 1 plus I. Have you just given up on typing it? Dad, you're still going with it.
No, I figured it out.
Okay, what was the deal?
No,
You're smarter than I am.
I just put it in
You
a
put it in a
different
new
folder.
July. Okay,
Yeah.
great. That was mysterious. Okay. So after you malloc something, when you're done with it, you need to free it for the memory leak reason. When you do malloc, it's like grabbing some space, grabbing some RAM, and then you need to free it to let the operating system do something else with it if it needs to. So we had something that we malloced way up here called SZnew. We're going to free it now that we're done with it. So up here underneath our do while loop, before our NA1 and all that business, I'm going to do free SZnew. And furthermore, to tell myself I better not use that space anymore because it's still got a memory address. It doesn't change SZnew, it just releases the memory. So now it's pointing to like a house that's been blown up. It's an address on a street, but the house is gone. The demolishing team came. So we need to change the address to point to 0 to tell ourselves, oh, you can't use that. Because otherwise, if we tried to use SZnew, it would still let us use it. We could still copy data out to it.
but we're copying data into memory that's no longer ours. So by setting it to null, and it should be capital null, sorry about that. By setting it to null, if we then try to do something with it like this, sz new subscript 0, I'm going to erase this, or something like that. If we try to do that, we would get a runtime error because sz new is pointing to null, and so we would be trying to write to a null memory address, and C will catch that. Whereas if we did not set it to null and we tried to write to it, it's very likely that it would let us do it, and it's also very likely that we'd wind up corrupting some memory. So in general, you want to free and then set to null anytime you're done with some memory.
Can you just do equals 0, or do you have to do null?
Either one works. The reason people use the word null is just because it burns into your brain. Oh, I'm dealing with memory there, right? But if you know what sz new is and you know that 0 is equal to null, both of those are totally cool. So down here, write a free statement for PNA1 and then set it equal to null. Free PNA1. PNA1 is equal to null. And just for giggles, let's try setting PNA equal to something. So star PNA1 is equal to 33. I just want to see it blow up. I want to see an error. That's why I'm putting that there, and then I'm going to remove it. GCC minus wall T2.C dot backslash A. All right, and see, when it tried to write to that area, it blew up. It said segmentation fault, core dumped. Sounds really bad, but if you look at it, somewhere in here there's a core dump file, which if we were gods, we could look and we could examine it to figure out what was wrong with it.
But we're not gods.
No, not yet, not yet. Okay. Now, if we hadn't set it equal to null, would we have gotten that error? Would we have gotten that indication that something horrible happened? I commented out that assignment to null so that when I run it again, it doesn't let us know that something has gone wrong. That's why you should always set your pointers to null when you're not using them. When you create a pointer, set it equal to null if you're not going to set it to anything else. When you free it, set it equal to null. All right, so I'm going to comment this out. We don't really want to do this. So where were we? This is just repeating some stuff that I've already mentioned. String cat will copy string 2 into string 1, but danger. If the resulting string is too large to fit into the string array, then an out-of-bounds memory overwrite will occur. And if you're lucky, you'll get told about it on the spot. If you're not, then memory will be corrupted. The program may keep running and produce invalid responses. It's better for a program to crash than to keep running silently in some kind of error mode. Doesn't sound like something you want, but you really do. You'd rather a program die than continue to run incorrectly, corrupting memory. So string comp compares two strings to find out whether they're the same or different. They are compared character by character until there's a mismatch. If the two strings are the same, it returns the value 0. So you just do string comp, string 1, string 2, and then if the result is 0, it worked. If they're not the same, it returns the numeric difference between the ASCII values of the two matching characters. Do you usually want to know that detail of information? No, just know that it returns less than 0 if string 1 is less than string 2, and greater than 0 if string 1 is greater than string 2. Now let's put that into our code just for some reason. Let's create two strings. String A is equal to hello. String BB is equal to goodbye. Let's find out if those two strings are equal. Int equal equals string comp CMP AA comma BB.
Wait, hold up. You can't use string like that, can you?
No, you can't.
There.
Well, I don't even know what I'm doing there. I was thinking
I
in
did
C.
that too. Like I typed it in, I'm like, no.
Yeah. I blipped into Java or C++ mode. That would be bad. Here we go. Get rid of those strings and replace with a word character. Thank you. It's funny that the compiler, well, the editor thought that that was an okay term. When it's not, it would not have compiled. Okay, and so now we've checked to see if they're equal. If equal is equal, all right. If equal, yeah, 0, printf %s matches %s \n end quote comma AA comma BB. Else, if parentheses equal less than 0, I'm just going to copy that print statement and paste it and change it to less than. %A less than %, like that. %s less than %s. And then our final one would be else if, and we don't really even have to do the if, but I'm going to throw it in there anyways. And make it say %s greater than %s. Compile it, run it, and it says that hello is greater than goodbye. Now how's it judging that? Because H is further along in the alphabet than G. The ASCII value of H is higher than the ASCII value of G. And lowercase letters are considered larger than uppercase letters, which is counterintuitive. So if we made this hello uppercase and we made this hello lowercase, it's going to say that hello uppercase is less than hello lowercase. Recompile, rerun it. Yep, it says hello with an uppercase H is less than hello with an lowercase. Now just to make sure it's working at all, I'm going to make the two words the same. Hello and hello, exactly matching. And there we go. Hello matches hello. And could we have written our own string compare function? Yeah, we could. We just have an index counter that goes until it finds a null, checking, both arrays. And then if it got to the end without ever having found a mismatch, it was good. We could write that function, but they already gave it to us, so let's not.
Yeah, you said string compare gives you like either negative, a 0, or a 1 or something.
Right. So here's what the loop looks like. We have two strings, SC1 and SC2. If we were going to write our own, int string comp char star SC1 char star SC2. We need some kind of counter. Int I is equal to 0. And so while SC1, except we're going to reference it as a pointer. I guess we could reference it as an array. We've proven that it works either way. While SC1 subscript I is not equal to 0, while we haven't found a null yet, and SZ2 subscript I is not equal to 0, then we're going to compare the two values. Let's call it difference. The int difference is equal to SC1 subscript I minus SC2 subscript I. And if difference is not equal to 0, then return the difference. Else return 0. Like that. That's pretty close to what it's doing. It's checking each character, and if they're the same character, great, it keeps going. Okay, and I forgot to do I++. But when it finds characters that don't match, it takes the difference between it and returns the difference. So it's comparing the ASCII value. And for example, if SZ1 is an uppercase A and SZ2 is an uppercase B, well, A is a 65, B is a 66. 65 minus 66 is a difference of 1, so it's going to return a negative 1. That makes sense?
So when you return the return value, how does that work for strings? Because it only returns 1, right? Does it just return the last difference?
Once it finds a difference, it bails. The first character that's different, it bails out because I do a return right
So
inside the loop.
What was the point of our prints that had less than? And was that just saying the
Because it's gonna
value of the character is less than?
Yeah.
Okay.
At a certain point, one character is either less than or greater than the other, unless they're all equal. Yeah. Now I'm not going to paste that in and get it to work and stuff like that. Something you may wonder about is what happens if the strings are of different lengths. And I can't promise that my code would work for that. So I'm not going to fix it.
Yeah, that would be bad.
Code for string comp function.
I was just doing all this code.
So we're going to find out what the gods look like, right? If it would actually show us. That's not how we do it. Oh, come on, show us this code. Okay, here it is. Isn't that fancy? I like mine better, but mine's not correct. I can't guarantee mine would work for strings of different lengths. You can see what I mean by the advanced programmers doing things like incrementing the pointers or incrementing counters right inside the for loop. And I'm sure they have a very darn good reason for doing that. It's because they write very terse code. Oh, and check it out. Here we're using the ternary operator. This is not working the way that we just read. It's always returning a negative 1 or a positive 1 rather than the two values subtracted one from the other. But good enough.
So didn't you say that's like ifs?
Yeah, that's an if.
Oh.
So if this character is less than this one, it will return a negative 1. But if this character is not less than this one, it would return a positive 1.
That looks pretty useful.
So we've talked about string copy. We've talked about string length. All it does is it counts the number of characters before the null and then returns that.
So right there, those stars like in the mallet, is that times or is that a pointer?
That's multiplication.
Okay.
Because we have to take how many elements we want multiplied by their size. If a character took 10 bytes, that would be 4 times 10. Yeah, it starts throwing way too many asterisks in there, but yeah. So when you're creating a new array with Malloc, remember to add 1 to it to account for the null. Here I added 2 because my code on the next page not only took the first name and the last name, but it concatenated a space as well, like this. So string copy the first name into full name, string copy a space, string copy the last name. So how long is this array total? It's equal to the length of that plus the length of that plus an extra 1 for the space plus 1 for the null. So Malloc can be used for arrays of any type, not just strings. Let's Malloc an array of doubles. We've already done ints, and I don't even know if we need to use this array of doubles, but why not? Double star DA. I should assign everything null as I created, or 0, but you don't got it because we're going to then just turn around and call malloc on it. DA is equal to, let's be awesome and # define our DA length as 800. And so DA is equal to malloc parentheses DA underscore len star size of double. Now we could access it via a loop. For I is equal to 0, I is less than DA underscore len, I plus plus, and then do something with it. Just store some value in it. DA subscript I is equal to, 100 times I, some silly value. And again, we could have used pointer nomenclature to access it. There's absolutely no difference. The compiler will change them both to the same underlying syntax. I guess we could print it out for our own giggles. I'm just going to copy this for loop and then do a print. With it being 800 characters long, this is silly, but we could change that. Printf, %f, because it's a floating point, space, end quote, comma, DA subscript I. And then free parentheses DA, DA is equal to 0 or DA is equal to null. Oops, my mistake. All right, there's my 800 numbers. I think I'm going to change DA length to 8. So in that one program where I was asking you to let it enter 6 numbers, you could use malloc. You could ask the user how many scores they wanted, and then you can malloc it out to the size that they want. So the first thing that the program could ask for is how many scores, or how many GPAs. So then you get that input back in with scanf, and they wanted to do 20, then you malloc it out to 20 times the size of an int or double or whatever size, whatever data type we were using to hold the data. Are we good, or do we need more typing time?
Can you scroll up for a sec, like back to where you had like a array of like two numbers? You're right there. That's 66.
Yeah.
33. So if you just put the 66 there and you didn't have a second one, all the elements now the array would be 66?
No, what it does is it assigns it as far as we've got there, and then the rest of them are 0.
Oh, okay.
So the first two are right.
So when we do 0, we're not making them all 0. We're just making the first one 0, but the rest are just already 0.
Exactly.
Okay.
Right. That's why. Yeah, so if we do that, they're all set to 0 because the first element gets set to 0, and then by the miracle of whatever happens, the rest of them are all set to 0 as well. But if we did that, then the first element's set to 66, and the rest of them are all set to 0. And if we do that, then the first one is 66, the next one is 33, and the other 8 elements are all set to 0. It's kind of misleading, right? Because it makes it look like if we did that, that if we change that to 10, they'd all be 10.
Yeah, that's what I thought it were.
Yeah.
Empty dreams.
Please go back down.
So you know how you have like 2D arrays and stuff like that? Are those just arrays of arrays?
Exactly. Yeah, a 2-dimensional array is an array of arrays.
Array of array of array of.
Yeah, and a 3-dimensional one would be an array of arrays. It starts to hurt your brain. But also, let's get down here. As we mentioned, you always want to free your pointer and then set it to null. The reason you set it to null is just to force the program to have an error if it ever tries to access the memory at that address again. So the textbook comments this, I kind of agree. One of the most challenging topics in C is pointers, yet they are what makes C one of the most robust languages in the computing industry for building unparalleled, efficient, and powerful programs. They're paramount to understanding what C has to offer. Despite their challenges, keep one thing in mind. Every beginning C programmer, including myself, that's the author, but me too, has struggled through pointer concepts. Kind of a rite of passage for any C programmer. So what is a pointer? It's a memory address. So say we have an integer variable called iResult that contains 75, and it's at memory address 948 whatever. Now say we have a pointer variable called myPointer. It does not contain a data value, but contains that at memory address 948 whatever, which happens to be the same memory address of the variable iResult. So that means that the pointer variable, myPointer, indirectly points to set the value of 75. It takes 2 steps to get to it rather than just one for us, not mentally, not the computer. The concept is known as indirection. It is an essential pointer concept. It's using indirection to get to that value. So the pointer does not really contain data per se. It contains the memory address of that data. So why use them? A pointer enables us to access a variable that is defined outside the function. When data is passed to a function via pointer, that function can change the data. That's how scanf works. And you use pointers to store the result of Malloc. So the actual location of a variable in the memory in the system is system dependent. The address of a variable is not known to us. So at runtime, the program has to figure it out by using the ampersand operator. We've already seen the ampersand being used for scanf. Putting an ampersand in front of a variable returns the address of that variable. So P is equal to ampersand quantity. That's assuming that P is a pointer. And that quantity is a variable, and we're picking up the address of it and storing it in that pointer. So just remember ampersand is meaning address of.
So you don't have to put star P?
When we did, this doesn't show the declaration of it. Somewhere these 2 variables were declared, right? Float quantity and then float star P. If you put star there, then you're not picking up the address of it. You're recording that address and trying to write it to null or whatever memory that is referencing. Remember that if you put a star in front of a pointer, it doesn't store value into that variable. It looks up the address that that's pointing to and then writes to that memory address.
Why do you have to declare pointers with type if it's just a memory address?
It is, but certain memory types take up more memory than others. So it needs to know whether it's a double, which takes 8 bytes, versus a float, which takes 4 bytes, versus a short, which takes 2, versus a character, which takes 1.
So the pointer doesn't just point to a start, it has like the whole space where it can, like it has like the whole like 4 bytes or something like that.
Yeah, a pointer is 8 bytes long, and honestly I don't know how the compiler knows. Well, I guess the compiler, as it runs, it creates a table of all the pointers and what type they are. And then so when the compiler is creating machine language, it's checking that. And then when we did that star parentheses P+1, it knew what type P was, and so it knew what that +1 meant, and whether it was supposed to be jumping by 1 byte or 2 bytes or 4 bytes or 8 bytes. But that's why we had to give it a type. There is a such thing known as a void pointer. A void pointer is just a pure pointer. We don't even know what type of data it's pointing to. But then you better cast it to the pointer type of your choice. If it's an int, you better cast it to an int star. So once a pointer variable has been declared, you can point to variable using the assignment statement like that. P points not to quantity but to the address of quantity. It contains the address of the quantity, known as pointer initialization. Before a pointer is initialized, it should not be used. Often it is initialized as it is declared if you just want it to refer to the same thing. Int x star p is equal to ampersand x. Now if I was writing this, and I did, so I don't know why I didn't do it, whenever I refer to a pointer, I use the same variable name and just stick p in front of it. And then when I'm assigning values to it, anytime I see a p, I know that I'm going to prefix it with a star, unless it's doing something special, like getting the address, getting the ampersand value of something, or getting the return value of a malloc. But if I want its value, then I access it with star px. You know, print that out, add it to something, whatever. Not xp. Experience points. There we go. So one of the greatest benefit of using pointers is the ability to pass arguments to a function by reference. By default, arguments are passed by value in C, which involves making a copy of the incoming argument. C is a pass by value or a pass by copy language. Depending on the storage requirements of the incoming argument, it may not be very efficient. Oh, here we go. Here's a function written that'll add two numbers and return their sum.
When it runs, this double and this double have to be passed in. They have to be copied. So the program's got to allocate enough RAM, it's got to allocate two variables, and then it's got to copy 8 bytes into each one, and then it's got to reference them before it can return them. If we declare them as pointers, we have a pointer to a double and a pointer to a double, and then we add the contents stored at those two memory addresses, then it's not allocating additional memory for the copy of the data. It's just allocating position for the variable itself. This had to allocate a value for the variable itself and then the data that it was being assigned to. So the second one is more efficient, which it's claiming is a misspelling, and I believe it.
So it's faster, but doesn't that seem like irresponsible? Because what if your memory gets corrupted?
Well, if you're a good programmer, then memory is not going to get corrupted. But it's a valid point. Yeah, using pointers is inherently risky, which is why the vast majority of languages don't let you do that. And so if you're writing C programming and you don't care much about speed, then you're not going to be messing around with pointers like that. I never would have written an add function that took two pointers and dereferenced them in order to get to some of them. But if I was trying to squeeze every last nanocycle out of my processor to run it at the, if I was writing a graphics library for a graphics card and I wanted to be able to run it, 100 frames per second rather than 98, then I might make little changes like this to speed them up. And it becomes more important the larger the data size. If instead of a double, this was a structure we had defined that had 2,000 different items in it, then it takes a huge amount of memory time to copy all 2,000 pieces of data in to that variable, and then copy 2,000 more. And so you can get dramatic speed improvements if you're dealing with structures by passing those structures in as pointers.
So if you used your pointer and they changed the actual value in the memory, it would just put out what you changed, huh? Like let's say you added two numbers and one was like 4, but you changed it to be 5, like in the memory somehow?
Right. It's still going to add up the two numbers, and one of them would be 5 at that point. If I understand what you're asking, I have 2 copies of those functions for some reason. If I did this before they were added, D1 is equal to 300, then yeah, it would add 300 to whatever D2 is. But if down here I change star PD1 equal to 300, then not only would it return 300 plus the value referenced in PD2, but the contents of that variable would now be 300. So the calling code would have its data changed to 300, just like scanf. That's how scanf passes its data back.
I meant like with like a hex editor.
Oh, well, yeah, if you're reading data, if you have an executable and you use a hex editor on it to find a specific byte and change it, then yeah, it should be changed for your program. Yeah, hex editors are fun. Okay, so C reserves extra memory space to make a copy of the variables x and y. And the copies of x and y are then sent to the function as arguments, which takes additional processing cycles. Passing arguments by value is not the most efficient programming means. Passing copies of two integers may not seem like a lot of work, but C programmers strive to minimize memory use and processing time as much as possible. Otherwise, why are you using C? Guess that's what they're saying. So also, when C passes arguments by value, you can't modify the original contents and have it take place down in the code below. So we're getting close to the end, but let's go ahead and write some functions that use pointers. So I'm going to go up above main, and let's write a function that multiplies two values together and passes the value back as a pointer. Since it passes the value back as a pointer, I don't even need to have anything returned. I don't have to have a return type, so I'm going to declare it as void. And I'm going to call it mult_p, and let's take doubles. So double star p result, and then double d1 comma double d2. And so we're going to multiply d1 by d2. Let's do double result is equal to p d1 times d2. And then let's store the value of that variable into the RAM that pointer represents. So star p result is equal to result. Now, we didn't have to do this intermediate step. We could have just done this. P result is equal to d1 star d2. And get rid of that temporary variable. And if preserving RAM and speed is the ultimate end all of using C, like the book keeps implying, then yeah, that's more efficient. So let's just do that. So now we're ready to call that. Let's declare three variables. Double DA, double DA, DB, DC. Now DA is equal to 100.1, DB is equal to 200.2. We're not going to assign DC a value, but we're going to call mult_p and pass in the address of DC. Address being the ampersand. So mult_p, parentheses, ampersand DC, DA comma DB. And could we pass in DA and DB by pointer as well? Yeah, we could, and then we'd have to put stars here when we access them, and the code would look really nasty. But we could for maximum speed. But this, I just want to demonstrate the syntax of passing this variable in by its address so that we can change it.
Oh, that makes sense. So if it wasn't a pointer, you'd have to have a return statement?
Exactly, you'd have to have a return statement. And yeah, sure, you can use a return statement. There's no reason not to. But what if you need two different values passed back?
Well, you can have more than one return statement.
You can have more than one return statement, but you're still only passing one value back. Python lets you do return 3, 34, and then you have two variables being shoveled back on the stack.
Oh, that's not how more than one works, is it?
Yeah,
I see.
yeah. So we could have like return 100 and then followed by somewhere else it'd have return 200, but if it hit the first one, it would return without getting to the second one. So if we want to pass multiple values back, you pass them in as ampersands. And one common technique is to return an error code. If this function returned 0, if we took the void out and made it return 0, then it worked. And if it returned a non-zero number, it's an error code. So you check the return value of mult_p to find out whether it worked or not, and then if it worked, you check to see actually what your data is. That's a very common way of handling it.
So you said C is passed by value, but pointers are references?
Well, pointers are still values. It's just getting the value of a memory address. It's like it's like I wrote down a mailbox number and handed it to you on a piece of paper. I'm still giving you a copy of something, but you know which mailbox to go and modify.
So what does pass by reference mean then?
Pass by reference is something that C doesn't do.
Yeah, I understand.
But C++ does. In C++, you can do this. Void, and you have a function, and you define a reference like that. And then in here, you have A is equal to 300. And then down in here, this is not going to work. When I called foo, and I passed in some variable, like this, int x is equal to 3, whatever. What this says is don't copy the value that's in x. Pass that variable in itself, including its address. So at this point, this variable and this variable are the exact same thing. Java does not do that. Python does not do that. C++ and C# do. You can do that with the ampersand operator. Except C# doesn't do that. You use the ref keyword, something like that. Now you could design a language where you had to pass everything in by reference and it would just work. But then how would you pass in constants? Like pass in 300 there. Because that 300 is that, and then what we're, or we passed in 1, foo parentheses 1. And then when we got up here, this was equal to a 1, great, A is equal to 300. What are we doing? Are we overriding some constant that was 1, now it's 300? It doesn't make sense. You can't pass in a reference to a literal. And a compiler that supports references will give you a compilation error when you try to do that. Otherwise, all these languages are doing is pass by copy. It's doing pass by copy either of the data or of the memory address. Alrighty, so we did not make it all the way through the PowerPoint, but we know more than what that's indicating because we've already talked about all this stuff. So I'm going to give you the homework anyways. Yay me. Okay, so I want you to do problems 1 and 3 from the chapter. I'll copy them and I'll paste them into a Word doc. So just hit your book, look at them, but I'm also going to have it in the homework document. What one of them is it's creating an array of events and then filling them with random numbers. But it's the function that has to fill them in. So you're going to pass the array in and you're going to process it that way. And then the other part of it is just create an int, create a pointer to that int, and then change it. That kind of thing. It has like you do 10 little tasks like that. All right, let's make a Dropbox for ourselves.